Assalamu alaikum everyone. Hope all you guys are doing very well. Welcome to another lecture of load bearing design 1. Today we are going to discuss that how we can find bending moment and shear force diagrams and what is the purpose of finding these diagrams and how they can help us to make our structure more stable. Let's discuss first about the types of bending stresses. Bending stresses are those that bend the beam because of either the beam's self-load or the external load or force that is acting on it. So bending stresses can be of two types: pure bending stresses or simple bending stresses. What is pure bending stresses? Bending will be called as pure bending when it occurs solely because of coupling on its ends. Here the coupling is referred to the bending moment M. So the pure bending is that bending moment is going to occur only at the ends of the beam, here and here. In that case, there is no chance of shear stress in the beam, but the stress that will propagate in the beam as a result will be known as normal stress. It will be called normal stress because it will not be causing any kind of damages to the beam. Whereas the simple bending includes the bending due to the self weight of the beam plus the external weight or load that we have applied on the beam. This type of bending is also known as ordinary bending, and this type of bending results both shear stress and normal stress in the beam. Because normal stress was already present in the beam because of the pure bending. Pure bending is always there, but simple bending is introduced as soon as we introduce external forces on the beam. Just in case if you have forgotten about the bending moment that we studied back in grade 11 and 12, let's discuss it again. So a bending moment represented by Bm is a measure of the bending effect that can occur when an external force is applied to a structural element. So you see, this is the normal beam, and if an external force is applied on it, it bends. So how much is the bending when a particular amount of force is applied? That is called bending moment. This concept is important in structural engineering as we can use it to calculate where and how much bending may occur when forces are applied. The most common structural element that is subject to bending moment is the beam, which may bend when loaded at any point along its length. To calculate the bending moment, the magnitude of the force F is multiplied by the distance of the force, which we denote by D, from the point of support. For example, if we see in this picture, this is an example of a simply supported beam. The load is almost right here in the center. So this is the force F, and if we wish to see that how much is the bending moment occurring over here, we have to see where the support is. So we always start the distance from the left side, therefore we are going to consider this support. So here is the support and here is the force right in the middle of the beam. So the distance of the force from the point of support, this point is going to be distance D. When we are going to multiply both of these factors, we will get the bending moment that is occurring on this point. Here another example is of cantilever beam, which is supported from one side. The force is acting on the other far end of the beam. Now if we wish to calculate the bending moment that is happening here, we have to multiply the load F with the distance from the support till the load D. This is going to give us the total bending moment within this cantilever beam. Now let's talk about the fact that why some structures are a failure. Why the failure occur in those structures? This is because of the bending when the stress exerted by a force is equivalent to or usually greater than the ultimate strength of the element. There are three types of failure in structures. First of all is the sudden failure. This happens in the brittle materials, which would continue bearing load, but they won't give you any kind of warning, and all of a sudden at a particular time they are going to break and they are going to collapse. Then we have progressive failure. We can see this type of progressive failure in bridges. Progressive failure is the spread of an initial local failure from a structural element, resulting eventually in the collapse of an entire structure or a large part of it. You might have seen that there are some bridges which are sagging, but a bridge is not meant to be sagging at all. So that sagging thing, that bending thing, is giving us a warning that this bridge can collapse anytime. So this is the progressive failure. And then the third type is that there is a possibility that the failure that took place in a structure is not 100%. So half of its failure was sudden and half of it is progressive failure. So the combination of these two become a partial failure of a structure. Efficiency of structures. In terms of efficiency, the structures are of two types. First one is the efficient structure. The capability of structure to use less material is termed as efficiency of structure, whereas the structure, if it uses more material, will be termed as inefficient structure. You may be thinking that a longer span structure will definitely consume more material as compared to the shorter span structure, but that does not make them an inefficient structure. We will see that what other factors are involved in making a structure either inefficient or efficient. So it is not necessary that the structure which uses less material is always more economical. For example, pre-stressed technique is to use less material, but it costs high for its maintenance. But in case of RCC structure, material used is more, but its maintenance cost is very less. There is a word that we use in a project. That word is time. So for every project you are given a particular time for its beginning and the finish. The building is more economical when you are taking into account the time factor, because when we talk about practical life, the time of construction, labor, and technical and non-technical sides are also part of it, which also make a structure efficient or inefficient. So why do we need to find a bending moment diagram when we wish to see if the structure would be efficient or inefficient? Because we wish to see that the basic load carrier unit, which is supposed to be a beam, is that an efficient beam or inefficient beam. Because if within a beam there is an insufficient resistance, that would imply that the beam will show some kind of movement. In bending moment diagram, we take the cross-sectional area of the beam and see that whether the material is fully utilized near the support or not. So this is actually the insight of the beam to give us an idea whether that beam is going to be an efficient beam or the inefficient beam. So far we have been talking about a rectangular beam. So now the question comes that if we have already established that a beam of a particular length is an efficient beam, would that same beam be efficient enough for the long span structure? Say if that beam was efficient for like 15 feet span, would the same beam would be efficient for the 30 feet span? In case that we have to make that beam efficient enough for 30 feet, we have to increase the depth of the beam. By increasing depth of the beam, we are actually adding more material to it, and there is a possibility that the same beam can collapse due to its own shear forces present in it because of its own weight. And adding more material to the beam will cost us more as well. But in practical life, economy and structural efficiency don't go side by side. Most of the beams are made rectangular because they are cheap, even if they are less efficient. But in case of bridges and large span structures, the structural efficiency is more important. Therefore, instead of using rectangular beams which have more self-load, we have started making I-shaped beams or T-shaped beams. These shapes have less material, but they are very much efficient than the regular rectangular beam. Now let's see how do we find the bending moment and shear force diagrams for a beam. There are 3 steps involved in the calculation of the bending moment diagram. The first step is that we have to calculate the reactions at the supports of the beam. Okay, so we are considering an example here that this is a beam which has a length of 4 meter. It has pin support at point A and a roller support at point B. A force of 20 kilonewton is exerted on it right in the center so that it divides the total beam into 2 parts measuring 2 meters each. Moment at this stage is that they are equal to the force multiplied by the distance from a point. So the free body diagram which we have made here is showing that we have AY, which is a reaction in response to the force that has been exerted over here, and BY at the B support. Both of these reactions are vertical reactions. So we have to make sure that the bending moment which is occurring at the support A and at the support B, the sum of these 2 bending moments should be equal to 0. The bending moment occurring over here is actually the reactions AY and BY in response to this force. So our first step would be that we are going to consider that the sum of moments about point B and let it equal to be 0. We have just chosen here the point B. This can be done at any end of the beam. I personally would like to calculate it from the point A, but the given example here has done it from point B, so we are going to take it from point B. So the equation would be like that sum of moment at B is equal to 0. So what is the bending moment? Bending moment is the force, which is 20 into the distance from the support into 2 minus the AY. So if we solve this equation, we will get the answer for AY, which is 10 kilonewton. That means that in response to an external force 20 kilonewton, the support point A is producing a reaction of 10 kilonewton, which is in opposite direction to the external force. Here the sign convention that we have chosen is that of a counterclockwise movement, because it is always positive and the clockwise movements are always negative. So this is the most common sign convention, but you have to make sure that you always use the same sign convention throughout your whole problem. So now we have got our first equation for AY, but we need to solve another equation in order to find BY, which is the vertical reaction force at support B. So now our next step would be to find the reaction force at this point B. Assume that the sum of the forces which are acting vertically on the beam have a sum equal to 0. Remember that we have to include in this all the external force and the reaction as well. So we will get an equation like this, that sum of all the forces in y direction is equal to 0, which means that sum of AY reaction plus BY reaction minus the 20 kilonewton force. We have used this minus sign convention because the clockwise moments are always negative. Let's put the AY value here, which is 10 kilonewton, as we have already found in the previous equation. By solving this equation, we come to know that BY is equal to 10 kilonewtons. Here the point to be noted is that we again stuck to a sign convention, which was to take upward forces, which are actually the reactions, as positive, and downward forces, which was the point load right in the middle, as negative. So there we have it. We have used the two above equations, sum of moments equal to 0 and sum of vertical forces also equals to 0, and calculated that the reaction at support A is 10 kilonewton and the reaction at support B is also 10 kilonewtons. So this is a free body diagram showing what we have just calculated through equations. This makes sense as the point load is right in the middle of the beam, meaning both supports should have the same vertical forces. Now let's draw a shear force diagram. The best way is that we keep these diagrams over one another. This was the initial diagram that we were provided of, that just a beam with a 20 kilonewton force. Then we drew a free body diagram. Ideally it should to be over here, and this diagram below this free body diagram. So a free body diagram showing that what force has been exerted on the beam and what reactions are taking place on both the ends of the beam support. So now let's draw a shear force diagram. We can interpret the shear force diagram here from the free body diagram. It says that there is a reaction of 10 kilonewton right at the start of the beam. So at this start there is a force of 10 kilonewtons. As we have already taken into account the sign convention that the counterclockwise movements will always be positive, so here we go up till 10 kilonewtons. It should be 10 kilonewton instead of 0. Then this 10 kilonewton force remains constant till we reach the point where the point load is acting, 20 kilonewtons. Now the force of 20 kilonewton has a clockwise direction and we use negative sign for that. So for minus 20 we will come below the central axis of the graph. So from 10 till 0 is 10 kilonewton, and then 0 to minus 10 kilonewton makes a total of 20 kilonewton. Now this 20 kilonewton force is constant throughout from this point till this support. So this force of 20 kilonewton, which is actually minus 10 kilonewton on the graph, it remains constant like a straight line here till we reach the other support of the beam. Here again 10 kilonewton force is applied, which is positive, so we will go up and again we will reach at point 0. Does this diagram not show you that the sum of all the forces is equal to 0? We started from 0 and we have ended on 0 again. If you get any other answer other than 0, that means you have made some kind of mistake somewhere. Now it's the time to draw the bending moment diagram. To calculate the bending moment diagram of the beam, we must work in the same way as we did for the shear force diagram. We will start from here at the support and consider that x, which is the distance, it is equal to 0 here, and then we will move across the beam and calculate the bending moment at each point. So the first step is that you have to make a cut just after the reaction of the beam. For drawing a bending moment diagram, it is necessary that you put all the three diagrams over one another so that it's easy for you to see what was given to you, what was the free body diagram, and how the bending moment diagram is going to proceed. So when we cut the beam, we only consider the forces that are applied to the left of our cut. And in this case, we have only this reaction force of 10 kilonewton, which is acting in upward direction. Now, if you recall that the bending moment is simply the force into distance. The formula of bending moment is force into distance. So as we move further from the force, the magnitude of the bending moment will increase, and this magnitude increase will be shown here in the bending moment diagram. So putting the values in the bending moment formula, the moment we have here is force 10 kilonewton here into distance, which is x, so it's bending moment at x point is equal to 10x. Then we have to make another cut, which is going to be cut number 2, and it is going to be just before the second force. It's almost in the middle, but the force of 20 kilonewton which was exerted externally on it is not taken into account. Since there are no other loads applied between the first cut, which was almost here, and the second cut, there's a line missing over here, the bending moment equation will remain the same. This means that we can calculate the maximum bending moment in case we have the midpoint, which is 2 meters, because initially at the start of the numerical we assumed that the beam is of 4 meter length, therefore the midpoint is going to be the 2 meters. So in this case our x, this point is 2 meters. So by simply substituting x is equal to 2 into the above equation of bending moment, so bending moment at x point, this point, is equal to force, which is 10 kilonewton, into distance, which is 2 meters, and the answer is going to be 20 kilonewtons. Then we are going to make another cut number 3, just after the second force along the beam. You see this red line. So now from the free body diagram we can see that there are two forces that are acting on the left side of the cut. There is a 10 kilonewton support reaction and then a 20 kilonewton of external force acting downwards. So this force is going to be minus. So now we must consider both these forces as we progress along our beam. For every meter we move across the beam, there will be a 10 kilonewton meter moment, which is like till here we have already calculated that the moment till here is 10 kilonewton meter. So now we must consider both these forces as we progress along our beam. So for every meter we move across the beam, there will be a plus 10 kilonewton meter moment added from the first force and a 20 kilonewton meter from the second force. So after the point x is equal to 2, our bending moment equation becomes bending moment at point x here is equal to 20, because till here we know that the bending moment we calculated from our second equation, plus 10 kilonewton force into the distance. This is the distance x and here the distance is 2, so it is going to be x minus 2 minus the 20 kilonewton force into distance, again x minus 2. By solving this equation we get this answer, 20 minus 10 into x minus 2. The reason we write x minus 2 is because we want to know the distance from the point x is equal to 2 only. Anything before this point we are going to use the previous equation. Then the last cut number 4, again moving across the right of our beam and making a cut just before our next force. In this case our next cut will occur just before the reaction from the right support. Since there are no other forces between the support here and our previous cut, which was almost here, so there is no other forces between this cut number 3 and cut number 4, the equation will remain the same, which is moment at x is equal to 20 minus 10 into x minus 2. But now in this case we know the total length of the beam, which is 4 meters, and now we can easily substitute the x for 4. So now mx is equal to 20 minus 10. Instead of x we have substituted 4 minus 2, and if you solve this equation we get an answer of 0 kilonewton meter. And this makes a perfect sense because our beam is in static condition and it should have a 0 moment at this point when we consider all our forces. It also satisfies one of our initial conditions that the sum of moments at a support is equal to 0. This is how we draw a bending moment diagram. If you use a graph, it would be more easier for you to plot this from 0 till 20 kilonewton till 0 again. Okay, so in a similar way, we can draw bending moment diagrams and shear force diagrams for a number of other kind of beams, whether they are cantilevered beams or simply supported beams, or we can also use different types of loads that can act on the beam. The example we took for drawing a bending moment diagram is of the point load only, which was only one external force acting on that beam. But this scenario can be changed. It can be uniformly distributed load, or it can be partial uniformly distributed load and point load as well, or it can be a varying distributed load as well. But for now, you have to draw a diagram just for a point load, and that also acting on a simply supported beam. That's all. So thank you very much.